Hello, my name is Eduardo Mello, and I'm going to present my work on optimized autonomous driving and energy component analysis. I will start by presenting an introduction to this topic, along with some motivation for this research. I will follow it with some of the mathematical models utilized. I then will introduce a linear approximation of the optimal speed profiles and their energy component analysis. And then we will transition to the role of the acceleration in these optimal speed profiles and finish with our concluding thoughts. The latest developments and advances in transportation technology have created several opportunities for maximizing the sustainability in our transportation network. Some of them are the advances in autonomous driving, the high efficiency of electric powertrains, and the modern approaches for attaining situational awareness. The combination of these factors make optimal speed trajectories an attractive transportation strategy, since autonomous driving systems are capable of precisely executing optimal speed trajectories that utilize these high efficiencies of electric powertrains. Also, modern vehicles have much greater ability to, in real time, obtain situational awareness from about traffic and infrastructure through vehicle-to-vehicle or vehicle-to-interface communication, and also utilizing the vehicle's internal sensor suites. And this sets the stage for many advances in the area of transportation. Between the approaches that have already been taken to minimize the energy consumption of electric vehicles, I would like to highlight a few. The first one being green waves, that is when a vehicle tries to minimize the number of red lights it faces going through signalized intersections, utilizing vehicle information and infrastructure information. That is often coupled with eco driving, that is when a vehicle tries to minimize its speed variations and also the idling times and the number of stops to save on energy. Another approach that's used is one pedal driving, that is when a vehicle starts to use regenerative braking as soon as the driver stops accelerating or removes its foot from the accelerator. And finally, optimal speed trajectories, that in this case, a vehicle with at least level 2 of automation could use infrastructure and vehicle information to generate an optimal speed trajectory, an energy optimal speed trajectory to drive a specific segment of a road or street. And this could be the length between two signalized intersections, between two stop signs, or other traffic constraints like speed limits. In this presentation, we will focus on the dependence that energy optimum speed trajectories have on their air drag, rolling resistance, and kinetic energy components. We will demonstrate a theoretical analysis and simulations that highlight the relationship between the initial acceleration and these energy components. And we will also show that counterintuitive to what we think about internal combustion engines, high acceleration capabilities are advantageous for improving the energy efficiency of electric vehicles. Optimal speed profiles have been previously studied, and they were shown to save upwards of 50% of transportation energy. This brings the question of why do they achieve such high savings? In order to respond to this question, we will analyze a linear approximation of these speed profiles. There are two different types of optimal speed profiles. There is a 3-segment and a 4-segment one. We will focus on the 3-segment variant that is defined by an acceleration phase, a coasting phase, and a final braking. To analyze the savings, we will break down the energy components of this linear approximation in its power absorbing components. In order to calculate the energy consumption of the speed trajectories studied in this paper, we will use the following energy model. It's going to be based in the power at the wheel being the sum of all power absorbing components in a moving vehicle, that being the acceleration power, the air drag, the rolling resistance, and the hill climbing. We will assume the hill climbing to be 0 for our calculations, and multiplying that willpower by the efficiency of the combined mechanical and electrical powertrain of an electric vehicle, we can get the power at the battery. Integrating that power at the battery, we get the energy of the vehicle. Two different efficiency models will be utilized in the analysis presented here. The first one being constant efficiency for forward motion, and regenerative braking, mostly for analytical solutions, and efficiency maps that will be mostly used for optimization problems. A sample efficiency map is shown in this figure. And when we talk about optimization, we'll be referring to the solution of the problem shown here. The goal is to minimize the vehicle's energy consumption, the integral of the power, while maintaining a desired average speed and obeying speed and acceleration limits. As previously said, the energy component analysis will be based on the linear approximation of the three-segment optimum speed profile. In order to obtain this linear approximation, a few variables have to be defined. The first one being the distance traveled by the vehicle, the acceleration capabilities of this vehicle, and the average speed desired. From that, we can obtain the coasting deceleration and the duration of each one of the three segments. To calculate the braking deceleration and the duration of each segment, the equations shown in the screen are used. They are based on the sum of the duration of the three segments being equal to the total traveled time, the vehicle starting and finishing at stop, and the total distance traveled being equal to the integral of the linearized trajectory. Manipulating these equations on the left, we can obtain the times t1, t2, and t3, while the coasting deceleration comes from the air drag and rolling resistance expressions based on the vehicle parameters and the average speed. In the energy component analysis, we will assume no regenerative braking. That means that the energy consumption can be estimated by the energy consumption of the segment T1, where the analytical expression for it is shown in this slide. Here, we show the energy consumption of three trajectories, a distilled version of the FTP75, the closed form solution, and the optimized trajectory of same average speed and segment length. The calculations were performed for segments varying from 300 to 700 meters and utilized 85% of forward motion efficiency and no regenerative braking. By comparing the first two bars, we can see that the estimated energy consumption utilized the closed form equation gives you a very close energy value to the actual energy consumption of that trajectory. The third bar shows that the energy consumption of an optimized trajectory with the same parameters is always a little better than the closed form solution, while the fourth bar shows that the energy consumption of the distilled FTP75 is always much higher than the optimized or the linear approximation of the optimization in any of the cases studied here. The 300-meter trajectory from the previous slide is shown in here. We can see that the optimal trajectory and the closed form solution are very close to each other. The main difference is that the optimal trajectory utilizes coasting, while the closed form solution may be slightly accelerating or braking during the second segment of the trajectory. The majority of the savings we obtain come from the fact that the linear approximation and the optimization, for that matter, reach a much lower maximum speed, significantly reducing the acceleration component of the work realized by the vehicle. That's named W kinetic or work kinetic in the third graph. Also, these trajectories only utilize energy in the first segment of the trajectory, and in the second and third segments, the accumulated kinetic energy is utilized to overcome the air drag and rolling resistance. Looking at the third graph, the last bar in green represents how much of the kinetic energy was recovered to overcome these two other components, the air drag and rolling resistance. Thus, it works kind of a regenerative braking, but since it acts directly on the work at the wheels, it has a much higher efficiency than the actual regenerative braking. You can see that in the middle plot, while the typical trajectory utilizes energy for half of the total time, the linear approximation only utilizes a significant amount of energy for the first 3.5 seconds. This slide shows the energy breakdown for two more segment lengths, and we can see that the same trend happens for every segment length, with the linear approximation and the optimization utilizing much more of its kinetic energy to overcome rolling resistance and air drag. It was previously demonstrated that high accelerations can provide higher savings in energy optimum speed profiles. And since most of our savings come from the reduction in maximum speed, having very short acceleration periods at the beginning of the speed trajectory, we decided to perform simulations to analyze how this initial acceleration can impact the energy consumption. Calculations with estimated energy, constant efficiency, and efficiency maps were used. Here are 3 examples of trajectories used to analyze the role of the acceleration. The first one using 1 meter per second squared of acceleration, 6 meters per second squared for the second, and 10 meters per second squared for the third. The acceleration in each one of the study scenarios was then limited by the vehicle characteristics being used. In this analysis of the role of the acceleration, 2 efficiency models were utilized, the first one being constant efficiencies, where 85% of forward motion efficiency was used and no regenerative braking, and also efficiency maps were utilized. 2 vehicles were also considered, one based on the chassis data of a Nissan Leaf, and the second one based on the chassis data of a Tesla Model F. The efficiency maps for each one of those vehicles is based on the combined motor and inverter efficiency of the Nissan Leaf, and it's shown in these 2 plots. These plots were generated for the vehicle based on the Nissan Leaf with no regen braking and constant forward power flow efficiency. You can see that for short segments, the estimated energy consumption, the energy consumption of the closed form solution, and the energy consumption of the actual optimization are very close to each other. As the segment length increases, the optimization becomes better than the other 2 cases, but they are still relatively close to each other. We can also see that most of the savings are achieved by when the vehicle is utilizing half of its maximum acceleration capability. A very similar results obtained with the model based on the Tesla Model S with constant forward power flow efficiency and no regen braking. The optimization does even better in this case for longer segments, but the same behavior of most of the savings being obtained by half of the acceleration capability is also seen. This set of plots show a similar analysis, but with the energy consumption calculated while utilizing a speed and torque dependent efficiency map. The line in blue is still representing the estimated energy consumption, being identical to the previous set of simulations. In this case, the majority of the savings still happen by the halfway point of the maximum acceleration of the vehicle. For longer segments, the energy consumption is more linear than before, and the optimization does better than the estimated consumption for all accelerations, not only for high accelerations. However, the computation complexity of the approximated trajectory is significantly lower than the optimized trajectory, making it still an attractive implementation. A last point that's worthwhile mentioning is that the actual calculation of the energy consumption of the closed form approximation utilizes more energy than the closed form approximation approximated value in the 700 meters scenario. And that's because the approximation is a better fit for shorter segments than for longer ones. Finally, the vehicle based on the Tesla Model S shows a similar behavior to the vehicle based on the Nissan Leaf. However, in this case, the optimization for long segments start to have a large variation from the approximated linear trajectory. This happens because the Tesla has a much larger efficiency map for which the optimizer can take more advantage of the high efficiency operating points of the drivetrain. From these previous results, we can conclude that the 3-segment energy optimum speed profile can be linearly approximated, producing satisfactory results. We also noticed that the optimum speed profiles achieved their high savings mainly from the reduction in maximum speed and also from utilizing the kinetic energy to overcome the air drag and rolling resistance throughout the second and third segments of the trajectory. We also saw that vehicles achieved most of their savings around half of their maximum acceleration. And even though energy optimal trajectories can have a significant energy advantage of the linear approximation, which is especially pronounced for the more powerful engine utilizing the more complex speed and torque dependent efficiency model, the computational complexity of the linear approximation still can make them an attractive option for implementing them in the real world. Thank you for your attention, and if you have any questions, please don't hesitate on sending me an email.